Welcome back to our third and final segment. We're still discussing resistors in parallel. Now we want to verify, some of the results that we managed to get, and we've used those findings to actually predict, to say, okay, what exactly happens if we add even more resistors in parallel? What happens to the effective resistance in the circuit? Also, how does that in turn affect, the main current in the circuit? But beyond that, we also want to look at the two resistors, which are not identical. We'll have one of 2 ohms and another of 4 ohms. Obviously, the 4 ohm is double the 2 ohms, and also want to look at the current issue between those two, as well as the potential difference across the source and across each one of the 2 resistors, R1 and R2. Right, so we want to examine the results as well. It says here, in a parallel circuit, what do you notice about the potential difference, which is the voltage, right? The potential difference, which is actually the voltage, okay? So what do you notice about the potential difference, which is the voltage, okay? Or across the resistors. Now we want to look at the voltage across each one of the 2 resistors. Now we are saying that R1 is equals to 2 ohms, okay? And then our second resistor that will connect in parallel is equals to 4 ohms, okay? Take note that R2 is equals to 2 times R1, or R1 is actually equals to a half of what? Of R2. We are simply saying that take note of that, proportion between those 2 resistors, right? Okay, so we'll go to our circuit. We'll use a 6-volt battery whose resistance is negligible. And what does that mean? It tells us that all the current passes through the battery, and the battery actually, as the source of energy, does not provide any or offer any opposition to the flow of charge or to the current in the circuit. Then we would measure the voltage across the battery, which is our terminal potential difference, and across R1 and R2, right? Okay, so if we go to our simulation, okay, so we have our voltage across the battery while there is no current. Just to verify that as well, it's actually equals to 6 volts. So even because we are saying that this battery does not offer any opposition to the current or to the flow of charge, then we would ignore its resistance. Hence, we'll describe that in terms of the battery having negligible resistance, okay? So if we close the switch, okay, current starts to flow, okay? But remember, we need to have 2 light bulbs or resistors connected in parallel. So our R1, its resistance is 2 ohms, which is half that of R2, which is 4 ohms, okay? So now we want to measure the potential difference across each one of them. The current readings are already shown by the ammeters connected, for the current that goes through R1 and that which goes through R2. So if we look at the voltage across R1, it's exactly 6 volts, okay, which is the same or equal to that of terminal potential difference. Take note of that. Then how about the voltage across R2? R2 is double R1, okay? So R2 is 4 ohms, okay? And then the voltage across, or the potential difference across R2 is also equal to 6 volts. That's what we take note of. But also pay attention to the current. The main current through the battery is 4.5 amperes, while across through R1 is 3 amperes, okay? While that which goes through R2 is 1.5 amperes, okay? So that's as far as the measurements are concerned, okay? Now, we said that the R total, okay, V total rather, is equals to 6 volts, okay, all right? And then we know that V across R1, okay, is also equals to 6 volts, okay? V across R2 is also equals to what? 6 volts. But also there's something about current. The main current through the battery which is that current, okay? The total current is 4.5 amperes, okay? Current through, R1, which is current through R1 is equals to 3 amperes, okay? While the current through R2, okay, is equals to half that, which is 1.5 amperes. So that's as far as the data that we need in as far as, you know, analyzing these results, okay? So, okay, this is what it is. The total voltage was 6 volts, okay? And we also saw that the voltage across R1 is equals to the voltage across R2, as we have shown here, okay? Right, so this takes us to the fact that V total is actually equals to V across R1, which is also equals to V across R2. Right, that's an interesting observation in as far as potential difference. All right, what about the current? Okay, current main, which is that 4.5 amperes, is equals to the sum of the current through R1 plus the current through R2. Okay, but take note, the current through R1 is actually double the current that is through R2, okay? And the main reason is because of R1. R1 is 2 ohms, while R2 is 4 ohms. So for 4 ohms, what that simply says to us is that R2 actually provides a greater opposition to the flow of charge, okay, which is high resistance, okay? Now, R1, which is 2 ohms, which is less than the 4 ohms, okay? What does that say to us? R2 offers or provides, you know, lesser opposition to the flow of charge. Hence, it is a lower resistance. That's why if there is a lower opposition, lesser opposition to the flow of charge, there is more current because the opposition is actually lesser by comparison, okay? So that's a very important observation. Okay, where does this lead us in terms of the conclusions? When resistors are connected in parallel, okay, we know that the voltage remains constant. That's the main thing. We've already proved or verified that fact, okay? So in a parallel circuit, voltage remains constant. So the terminal potential difference is equals to the potential difference across R1. It's also equals to the terminal potential it's also equals to the voltage across R2. Hence, we say the voltage does not change as long as it is in a parallel circuit, right? Okay. Furthermore, okay, in a parallel circuit, let's think about what do you notice about the current in the circuit. Okay, if we can go back to that circuit, the one that we managed to get the figures. Okay, so the total current, which is that, okay, so the total current, which is actually equal to 4.5 amperes, that's our total current, okay? Now, that total current is split between R1, which is 3 amperes, and R2, which is 1.5. So if you add those two, they actually give you the total, you know, current in the circuit, right? Now, if we also look at the middle column, which is about the current, so our total, which is 4.5 amperes, okay, is equals to, you know, the 3 amperes plus the 1.5. And take note, R1 is less than R2, okay? Because R1 is less than R2, or R1 is equals to half R2, okay? This is another fact, okay? So where there is greater opposition to the flow of charge, there is actually greater resistance. So hence we have got lesser current in R2 than in R1, okay? So that's a very, very important observation from the data that we managed to obtain, okay? So we've also managed to measure the current, okay, from that goes through each one of those versus the main current that goes through the battery. So in short, we are saying that the main current through the battery is the sum of the current that goes through bulb number 1 and the current that goes through bulb number 2. Okay, so this is the main thing about, you know, this parallel circuit that we've just explored. Okay, and if you add the 3 and the 1.5, it gives you that total current, which is the main current in the circuit. right? Okay, right. So what conclusions can we arrive with regards to current in a parallel circuit? What do we know? The current is divided in a parallel circuit. So the total current is split between a number of resistors connected in parallel. Let's say, for argument's sake, okay, to generalize this, if we've got an n number of resistors that are connected in parallel, the total current will be split between those n resistors. So if you say current through R1 plus current through R2 plus current through Rn, it must give you the total current for those n resistors that are connected in parallel. Hence, mathematically, we arrive at this conclusion in as far as the total current being divided. But also, the largest current passes through the resistor with the smallest resistance. That's a very, very important, implication. Now, you realize that the 2 ohm had 3 amperes of current passing through it compared to the 4 ohm, okay, which had half that current, which is 1.5. So in short, what are we saying? The greater the resistance, the greater the opposition of flow of charge. Hence, we've got less current where there is greater resistance in a parallel circuit. And conversely, we are also saying, in a different way, that the resistor that has got the smallest resistance in the parallel combination will have the greatest current passing through it. Why is that so? Because we are saying that the smaller the opposition to the flow of charge, the greater the flow of charge, because there's actually lesser resistance. That's the main thing about the current. Okay, right. We've realized that the current through R1 is greater compared to that of R2, because R2 is twice R1. All right, okay. And then we also recall that resistance uses that equation. So it means for the same potential difference, the greater the resistance, okay, the smaller the current. So you need to understand that mathematical relationship as well, okay? Now, having said that, so for resistors in parallel, this is what we also notice, that for us to get the total resistance, we would actually consider the reciprocal of each resistor as a sum. But remember, this equation actually gives us the reciprocal of the total resistance in parallel. But we are actually looking for Rp at the end of the day, okay? Right, and then in summary, we understand that opposition to the flow of charge is actually the resistance, okay, of a component or a circuit. And the SI unit, which is the ohm, is actually equals to a volt per ampere, right? That's the main idea in as far as parallel resistors are concerned. So the long and short of it says, in a parallel circuit, current is divided, okay, while potential difference remains constant. And then this is how the equation that we would use to determine the total resistance in a parallel circuit for n resistors connected, for n resistors that are connected in parallel. Right. So after all's been said and done, the main idea that we want to get across is that in any parallel circuit, the effective resistance, as we add more resistors in parallel, the effective resistance will decrease. And in the process, current is going to increase. That's the time that we had for today, just to look over the concepts around, or exploring the concept around, parallel resistors. From myself, Themba Ncube, bye-bye for now.